Okay, good morning again. Any questions from the previous lecture? No? Okay, let's start again with this example where we left last time. We had a set of processes and the arrival time with also the CPU bus time for each one of them known. We did the example using first come first serve algorithm where we found their finish time, their waiting time, and turnaround time for each process. So let's do this example again using shortest job first and shortest remaining time job first algorithm. It will also help you wake up. So, okay, I'm not going to do example on the board. You have to do it on your notebooks. You have 2 minutes for doing the example using shortest job first algorithm. You need to find the finish time, the waiting time, and the turnaround time for each process using shortest job first. Please do the example so it will help you to understand the algorithm itself. By the way, has anyone watched the lecture which I recorded last time? Has anyone watched it? No. I was just curious whether the audience was able to listen me or not clearly because I was mostly standing there and laptop was there. Okay. Anyone who has solved the problem? Okay, keep working. I'm just like drawing it again on my own reference. Okay, let's do it together. And then maybe if you are halfway through your solution, you can please verify you are in the right direction or not. So we again have this timeline, and the time is starting at 0. We have A arriving at 0, here, let me do that is 5, 10, 15. B, C, and D, and we are using the algorithm shortest job first, right? So at 0, we have no other candidate, only one candidate, and its execution time is 30. So okay, and then when we are done at 30, we look again about at the ready queue. So in the ready queue, we have 3 more. So A is done. We have B, C, and D. Which one is the shortest one? B is the shortest one. So we schedule the B, and its execution bus time is 20. So it completes at 50, right? So now we are also done with B. So then at 50, we look at the available at the ready queue. C and D both are ready, and C has the smaller execution time or burst time. So we schedule the C, right? And 50 plus 10, no, 50 plus 12 is 62. So we get here C, and then we after that we are left with only one candidate or one ready process, which is D, and has execution time of 10. Sorry, execution time of 10, so it is 72, right? So A, B, C, D, finish time, waiting time, turnaround time. So finish time for A is 30, B is 50, C is 62, and 72, right? I don't need to write here, you can do it on your own. Then the waiting time for A is 0. As soon as it arrives, it is scheduled, right? And then for B, the waiting time is B arrives at 5, and it is scheduled at 30. So this is the waiting time for B, which is 30 minus 5, 25, right? So 0, 25, and C, it arrives at 10, and it is scheduled at 50. So this is the waiting time for C, right? 40. If I'm doing something wrong, let me know. And then for D, it is scheduled at 62, but it arrived at 15. So 62 minus 15, 52, and 47, right? Turnaround time. Has anyone found turnaround times? The only difference is that this time you will be taking the difference between the arrival time and the completion time, not the time when it is scheduled. For example, the turnaround time for A is it arrives at 0, it completes at 30, so it is 30, while waiting time was 0. Okay? Sorry? Okay. So you can do the same thing, let's say for D, it got completed at 72 and it arrived at 15, right? So 72 minus 15, 62 and 57, right? You can do the further remaining too. Yeah, go ahead.
What do you schedule B before C and D? They have a smaller execution time.
Say it again.
What do you schedule B before C and D if the others two have a smaller execution time?
Why I scheduled before B before C and D,
Yeah.
right? So B has the execution time of 20, the first time of 20. But B oh, okay. Why didn't you connect me at that time? Maybe I was looking at this one by mistake instead of looking at the first one. That's correct.
But when they execute, so they're all gonna be in the ready queue, so you can just select one already, the shortest one, right?
Yeah, shortest one. So the shortest one is the shortest one is to be selected at this time point 30. So all these three are ready, right?
And they're all ready.
So we need to select
So this is,
by mistake.
this is like the, first come, first serve.
This one?
No, and this is equivalent to the first come. first
No,
serve.
no, this is shortest job first.
Yeah, but what I mean is because you ordered A, B, C, D.
Yeah,
it's
yeah, so
equivalent.
I made mistake because I was looking at these server, at these numbers by mistake. But actually, what should I have done is to look at first time. Thank you for the question. Okay, at least it tells me that you are attentive. Okay. So now again, do the same example. And this is going to be little tricky or interesting. Do the same example using shortest remaining time job first. Shortest remaining job first, okay? Otherwise, I mean, the numbers are same, arrival times and the bus time is same, you just need to change the algorithm and then find these waiting times, turnaround time, finish time. Don't get confused from this one, so I'm deleting the waiting. Can look at the slide. Yes, go ahead.
If, passing on this example, like if the times are equal, does just the current process take precedent? Like
If the remaining times are equal, then you can you can select any one of them. So which basically mean that you don't give priority. Okay, again, let me start doing the problem on board, and then you can check whether the solution you have is correct or not, or my solution is correct or not. So we have shortest remaining job first, right? Okay, again, I think it's better if I first write the arrival time so that later on it's not confusing for me. A, B, C, D, right? And now I can ignore this one. I have it already. Okay. Here I'm building another table. Let's say A, B, C, and D to record the remaining time of each one of them. Okay. So at time A, at time 0, I have no other ready process. I have only A. So I schedule A and it has the total execution time of 30. Right? Let me also record it here. 30, 20, 12, and 10. So at time 0, I schedule this one. It executes for 5 time units. And so which means that now the remaining time it has is 25. And then at 5, I look what are the available ready processes. So I have A and B. So A has 25, B has 20. So this has shortest remaining time. So I schedule B. So I schedule it for 5 time units. And then the remaining time it has is 15. And now the available are ready one are A, B, and C. So the C has the smallest one, okay? So I'm picking C. So C executes for 5 time units, and so remaining one is 7 plus 5, right? Okay. And so now I look at again at the ready queue. So I see A, B, C, and D. The smallest one is still C. So I continue with C, right? So it executes for 5 more time units, so which basically means 22 here, right? And then this one is done, right? So this one is done. So then I look at the available are the ready processes. So I see 25, 15, and 10. D is the smallest one. So I schedule the D for 10 time units. So it will be 15 plus 7 was 22, 22 plus 10, 32. So here you get D, right? And then this one is done. Now again, I look at the available on the ready queue. I have A and B. So the smallest one is 15. So I schedule B for 15 time units. So 32 plus 10, 42, and 42 plus 5, 47. So I get B here. And then I am done with B. And I have only one ready process, which is going to take 25 more time units. 47, 57, 67, and then 72, right? A. Okay. Now you can find finding the finish times is maybe like easiest thing. So A is with the finishing at 72. Anything wrong with my statement before I go ahead? No? Okay. 72. B is finishing at 47. C is finishing at 22. D is finishing at 32. Okay. Waiting times. For A arrives at 0. Then it is scheduled for 5 time unit. Now for waiting time, you need to consider the time from the perspective of the given process, the time when it is not running on the CPU, right? So here, A is not running on the CPU, right? At all this time point. So what is the waiting time for A starting from this? Actually starting from here, up to this point, 47 minus 5. So 42. Waiting time for A is 42. For B, it arrived at 5 and got immediately scheduled, right? And then it was not running for this time period, which is 32 minus 10, 22, right? For C arrived at 10 and got scheduled at 10 and then it completed in one go, right? So its waiting time is 0. D, it arrived at 15 and got scheduled at 22, so its waiting time is this one plus, that's it, right? So 22 minus 15, 7.
4.
Right? Okay. And turnaround times. I'm doing this example, but then at the same time, I'm thinking it is taking too much time. We will be running behind the process. Anyway. So turnaround times, let's say do the turnaround time for one of them, not for all of them. Let's say we do for C. C is simplest one. Let's say do it for D. Okay. A. So A arrived at 0 and it got completed at 72. So it is also simplest one, 72. Okay.
Just arrival time minus finish time.
Yes. Finish time minus arrival time. Yeah. Okay. So this was like, this is the result for shortest job first. So you can, when you are done with the example, you can later on doing at home, you can verify whether your results are correct or not. This is for the shortest remaining job first. For example, the turnaround time in our case for A was 72, which is correct. And what we else had, we had 42, 22, 0, and 7, right? Okay. Now, okay, so before I talk about the next algorithm, so until now we have covered 3 algorithms: first come, first serve, shortest job first, shortest remaining job first, right? What is the good thing about first? Let's say, what is the bad thing about first come, first serve? The bad thing is that on average, it gives the higher waiting time, and it is less responsive because if you remember, if you consider a scenario where a longer job comes first, let's say with 100 time unit, and after that B comes, which has, let's say, only 10 time units. So what happens is that B will be stuck behind A, right? So the responsiveness for all the shorter processes will reduce, and their waiting time will also increase. So to handle this, we said, okay, we are going to schedule the processes based on a criteria, which is, let's say in the non-preemptive case, it is the shortest job first, right? So if we do the shortest job first, then what we have is that we avoid the shorter processes from being stuck behind the longer processes, assuming we know their burst time, right? But then it reduces the waiting time, but still the system is not responsive. Like if we have, let's say, a shorter job, B, with a time unit of 10, and we have another job with the same shorter job remaining time, then it will be keep waiting. So what we do is that we said now we are adding the aspect of preemption, and we came up with the algorithm of shortest remaining job first. Now, the bad thing about the shortest job first or shortest remaining job first is that we need a mechanism to estimate the burst time, right? And that will also be not a 100% correct estimation. We will try to be as close as possible. But we need an additional mechanism. So what we can do is that we can come up with another solution where we use the FCFS, but we add an additional trait or an additional characteristic to schedule the algorithm, where what we do is that to increase the responsiveness, we allocate the time budget to each process. And then still we are using first come, first serve, but then a process, if it is scheduled, it cannot be executed for more than the allocated time budget. If the allocated time budget is consumed, then it is moved back into the tail of the ready queue, at the tail of the ready queue. And another process from the head of the ready queue is scheduled, but it is again scheduled only for the given time budget. So in this way, what happens is you don't need an estimation mechanism for the bus time, and you also you may need the mechanism, but the thing is that you are increasing the responsiveness of the processes without waiting on the without depending upon the bus time itself. The main or the crucial thing here is your time budget which you are allocating. So in the examples, maybe we will be using the bus time for the purpose of the example, but bus time itself is not needed, because for the purpose of scheduling, you don't need the bus time. For the purpose of scheduling, you only need to know the time budget allocated to each process, which is independent of the bus time. Okay. So maybe we can first do an example again. We can follow the same format. We can do an example on the board, and then we can read the slides. So let's say we have again these four processes, and again I am giving the arrival time of 0. Let me think of a meaningful case. 0, and that's a 4. I want to make the quantum. Okay, let me take 0, 10, 20, 30. And bus time, I'm keeping it, let's say, 40 for each one of them. Okay. And we are using this algorithm, which I'm calling round robin. And what we do is it is similar as FCFS. The only difference is that you have allocated time budget for each process for execution, and that time budget is known as quantum. And let's say I'm indicating it by Q, and I'm putting the value of Q equal to 5, right? So what is my current ready queue? A, B, C, D, right? They arrived in this order. So this is head, and this is tail, right? So what I will do is that I will first schedule. Again, let me do 20, 30, A, B, C, and D, right? So I schedule A, and its bus time is at the time how long it needs to execute is 40. But we will allocate it only a quantum of 5 time units. So we execute it for 5 time units, and then we move it at the tail of the ready queue. But at 5, there is no other process yet ready. So only itself, right? So we can execute it again for more 5 time units. And then we move it at the tail of the ready queue. Now we have 2 processes ready. B is on the head, A is on the tail. So we can execute 10 again for 5 time units. So this was A, this was A, this is B. It will be executed for 5 time units and then move back to the tail. At this point, no other has arrived, only we have A and B in the queue. Now A is on the head, B is on the tail. So every time when you retire a process from the scheduling, you put it at the tail of the ready queue. So now B is at the tail, A is at the head, so A gets the turn. At this time, but after this, you again put A at the tail. And now what you have, and let's say that C is put on the tail before A. So your queue is the ready queue is this one B, and then the C arrived, and then A is retired, right? So next, which will be executed will be B again for 5 time units. Put it back. Then C will be executed for 5 time units. Put it back. A will be executed for 5 time units and so on. Right? You got the idea. Any questions? So, I mean, even if you don't know the burst time here, for the purpose of our example, for demonstration, we are just putting the value of the burst time. But even if you don't know the burst time, you can still use your scheduling algorithm based on the what is your quantum, and also what is the order of the ready processes in the ready queue, right? Any questions? Okay, so now let me read these slides. So here each process will get a small unit of CPU time, which we name as time quantum or time slice, which can be usually between 10 to 100 milliseconds. And after this time is elapsed, the process is preempted. So this algorithm is a preemptive algorithm. It is not possible that, like, for example, if you remember in FCFS, there was no preemption. Once a process is scheduled for execution, it will run for whole its burst time. Here, once a process is scheduled and its quantum is expired, then it is preempted. Okay. And added to the end of the ready queue, at the tail of the ready queue. So if there are, let's say at a given time, n processes waiting in the ready queue, then, and the time quantum is q, then each process will get 1 by n of the CPU time in a chunk of q time units. Okay. And no process will wait more than n minus 1 q time units. N minus 1 times q time unit. Let me finish this round robin, and then after that we can have a break. Okay. So what about the performance of round robin? Actually, the question is that how the performance of round robin algorithm is affected by the value of q or the quantum. So if quantum is large, let's say it is extremely large, let's say it is infinite. So then what will happen? This algorithm will behave same as FCFS. So for example, here, let's say we have, instead of 5, I have 500 or 5,000. So if A is scheduled, it will complete its execution until 40 because it still has the quantum is not expired, right? And once it is done, it will voluntarily release the CPU. After that, we will look what is the next available process in the ready queue. It will be B. So B will run for 40. C will then run for 40 and D will run. So it will become FCFS, right? So its performance will be same as that of the FCFS if Q is extremely large. On the other hand, if we go to the other extreme, if we have not actually the other extreme, but if Q is relatively small, then we will have good CPU sharing. For example, in the case where we were having the 5 Q value of Q was 5, then what we were doing is that the CPU was shared among the ready processes in a fair way, comparatively in a fair way. And one thing about, now the question becomes, okay, it is not good to have large or extremely large because it will become FCFS. And the small one gives us a good CPU sharing. But the question is that how small the value of Q should be? Is there any lower limit on the value of the Q? For example, can we make it 1 time unit or not, right? So what we found out, and I will explain after the break, that the value of Q must be large with respect to the context switch time. Otherwise, there will be too high overhead due to the context switching. There will be frequent context switching. I will explain after the break how. Okay. So let's have a 10-minute break, and then after that we can come back to the lecture. Okay, so in the break, we are going to do an activity, and the purpose is to break your bondage, which you have developed in the 8 week. I don't want you to sit next to each other. Like I see all these 3 students sitting next to each other. These students are always sitting next to each other. So starting from the person sitting in the front row, start counting from 1 and stop at 3, and next person again counts from 1 and stop at 3. Okay. So you can start counting from 1. No. 1. Yeah, now remember your numbers. Okay. Go ahead. Remember your numbers. Go ahead.
2, 3,
Yes, your turn.
2, 3, 2,
Your number.
1, 2, 3, 1, 2, 3.
Okay. Now all the people with number 1 should move to the last row. And then in the same way, people with the number 2 sit in the second last, to the number 3 sit in the third last, and so on.
Oh, I do.
It looks better. Now at least I will not be like, okay, I will not know this person is always sitting there and that person is always sitting there. So it will also like refresh my mind and force me to put some more energy and same for you guys. So maybe the person who was sitting here is now at the focus, now not at the focus. Okay. Okay, so maybe we can resume our lecture. So what we were talking about, we were talking about like is there any lower limit on the value of Q or quantum time size which is not for each process? And we said that it should be larger than the context switch overhead, or the time it is taken to complete the context switch between two processes. You remember how context switch works, right? So you need to store all the information of the currently running process into its process control block. And the process which you are going to resume, you need to reload its information from its process control block into the relevant registers, and then that process will start executing. So this process takes time, which is pure overhead, because you are not doing any useful work from the perspective of process execution. You are doing some management tasks, right? So the queue must be large with respect to context switch time, otherwise the overhead is too high. Let me try to explain it using an example. So let's suppose that you have a process and it has execution time of let's say it has execution time of 10 nanosecond or whatever, 10 time unit. And so this is like bus time, let's say, in our case. And the quantum you have is equal to 15, right? So let's say this process, let's say process A, it is scheduled for the execution. It starts executing at 0, it completes at 10, and the quantum is not expired. So from the perspective of this single execution of this single process, there is no context switch. It gets the chance to complete in a single go, right? Now let's say I half the quantum from 5:15 to, let's say, 7. Okay. So if that is the case, then at this time point, its budget or time slice is expired. So A get only this portion of time to execute, and then another process from the ready queue will be scheduled, let's say B, which basically means that here you have a context switch, right? So here in like this is not the ideal case. We are just trying to understand how algorithm works, but this is not the practical case. Practically, what will happen is that when we do the scheduling, we will not start executing immediately at 7, because there will be some overhead here, which is the overhead of context switch, right? So in our examples, we are assuming that context switch takes the 0 time, which is not the real thing, okay? Now, if I reduce Q even further, let's say I reduce Q by, and then here after that, let's say B get executed and it completes at, let's say, at 14, there will be another context switch, and let's say then A get the chance, right? Again, and now let's say A gets completed in 2 slices, right? So when Q was 15, there was no context switch. When Q was 7, A had to suffer from 2 context switches to get its execution completed. And now if I reduce it even further, let's say I set it to 3, so you will have a context switch at here. So after every 3 time units. So which means that A will face even more number of context switches for its completion. So as the more context switches mean more overhead, right? So the queue should not be extremely small. Otherwise, the overhead of the context switch will keep increasing, and it should be large with respect to the context switch. So, which basically means that, let's say that a single context switch takes 2 time units, right? So at least your Q should be greater than 2, at least. Even like if you put 3, it will be very bad choice, but if it is 2, every time you will be just having context switching, and no process will ever get the chance to execute. You will be only wasting all your time in overhead. One process A get context switched by process B, but before B gets the chance to run, it gets context switched by process C, and then it gets switched. So every time there is context switch. Okay. Any questions? Yeah, go ahead.
Can you clarify what bus time means?
Okay, so here actually we meant CPU bus time. So anyone who wants, you got the answer?
Sorry.
Okay. Okay. So we have already done an example. You can have like 1 minute to look at this slide to understand another example of round robin. Okay. Or maybe I can walk you through it. So you have three processes, 1, 2, and 3. Their bus time or CPU bus time is 2433. Quantum is equal to 4. So you assign the 4 time units of budget of 4 time units to each process. So let's say they arrive in the same order, like P1 arrives before P2 and P3. So you at time unit 0, you first execute P1 for 4 time units, then its budget is expired. Then you look at the ready queue. So the P1 moves at the end of the ready queue. Now at the head of P2 and P3. So you schedule P2 and it executes for 4 time units, but its total bus time is 3, which is less than, so it completes at 7, not at 8. So at 7, you again, so it is removed from the ready queue because it has completed. So then you look at the ready queue, at the head you find P3. So you schedule the P3 for 1 time slice, but its execution time is less than time slice. So what you do here is that it completes the execution at 10. And after that, what you do is that you schedule the P1, but after every time slice or every quantum of 4 time unit, there is again a context switch, right? P1 context switching itself. I mean, definitely this is not how things are done, but here we are just trying to convey the idea that after every queue time unit, you need to look, you need to check if there is another ready process in the queue or not, right? Any questions? So this algorithm will give you typically higher average turnaround as compared to shortest job first, but better response time as compared to shortest job first. So why better response time? Because you are making sure that not any given process occupies the CPU for more than queue time units. Unlike the FCFS, as you remember in FS, if you occupy, then it depends upon your burst time, how long you keep it, how long you keep the CPU. Any questions? No? You want to do this example, or you can do it at home? You can do it at home, right? We already had like 2 examples enough. Okay, so round robin compared with FCFS. So round robin is good for fast response time, but it is not good for turnaround time. We always want to have, for fast, we always want to have lower for response time and also the lower turnaround time. So the good thing about round robin is that it reduces the response time, but not the turnaround time. And here is an example. Let's say that you have 3 jobs and all of them arrive at time 0. And each has a CPU burst time of 10, right? So let's say that now, according to the round robin, how will you schedule them? A, B, C. You have 5 time quantum of 5 time units, okay? And then A, B, and C, right? So here, what is the turnaround time? The turnaround time for A is it arrived at 0 and it completed at 20, right? B arrived at 0 and completed at 25 here, and so on. So now look at the turnaround times of the same processes when they are scheduled using FCFS. So they arrived in the order A, B, and C. They all of them have 10 time units of the burst time. So A, B, and C. So the turn time of A is 10, 20, and 30. B 20 and C 30. If you take average, the average of this one will be lower as compared to the average of this one. Okay. So the response time is better here. Why response time is better here? Because here A runs and then it is not like B and C must wait for the A to complete. You are doing the time sharing among the processes, time sharing of the CPU among the processes. But here B and C must wait for A to complete. That's why the response time is here better. But the you get the better turnaround time in the FCFS. So there is always trade-off. There is no like most of the time it is very difficult to find a perfect solution which satisfies all your requirement. Okay. Any questions? The same thing which I have explained, how the relationship between the quantum and the context switch overlap. Okay, so I'm not going through this slide. Okay, so it is not true that if you increase the quantum time, your average turnaround time will reduce. What does that mean? What we want for the average time? What turnaround time is better? The lower is better, right? So it is not true that if you increase the quantum in the round robin algorithm, the turnaround average run turnaround for the processes will reduce. It's not true. However, the good thing, the thing which we keep to in mind is this: for a given quantum value and for a given set of processes, if there are larger number of processes which can complete within a single quantum, it means that quantum value will be better from the perspective of lower turnaround time. Do you get it or not? If larger number of processes can complete in a single quantum, then that quantum value is better for that particular problem or particular case. So you cannot say that always there is a relationship between the value of the quantum and the turnaround average time, right? Or not? Some faces look confused. So let's say I have the quantum value of 10, and I have the process A, B, C, D, and E, right? And let's say this has execution burst time of 15, this has burst time of 10, this has burst time of 20, this has burst time of 10, and this has burst time of 10. How many processes can complete in a single quantum if they get the chance to run B, D, and E, right? Now take another example. Let's say I change the quantum value, okay, and I set the quantum value equal to 5. So now if I change the quantum value to 5, none of them will get the chance to finish in a single go or in a single scheduling. So which means that turnaround time will increase for each process because they will be preempted by other processes before they complete their execution, right? But here, at least 3 processes will not be, if once they are scheduled, they will not be preempted by other processes before they complete their execution, right? So for this particular bus time, the particular case where we have the specific bus time for the processes and we have Q equal to 10, it is better to have Q equal to 10 than Q equal to 10. But what the point which I'm trying to convey is, let's say I increase the Q to 50, and I have a different set of processes where this is 20, this is 25, this is 20, this is 25, this is 20. I have increased the Q from 10 to 50, but still none of the processes get the chance, right? So it is not always the case that your turnaround time will increase. Will improve. So it is basically, the question is how many processes can complete in a single quantum. Any questions? Okay, so priority scheduling. Actually, we have already seen example of the priority scheduling, right? Can you give me some names for the priority scheduling algorithm out of what we have seen?
The short, I don't remember the name, but the
Shortest job first.
Yeah.
So shortest job first is a priority schedule because when we schedule an algorithm, we give the priority to the process which has shortest job, which has the shortest bus time, right?
You also mentioned longest job first.
Yeah, we haven't covered that algorithm, but I mean, that is also a priority-based algorithm, right? Even shortest remaining time first is a priority-based algorithm. The only difference between SJF and SRJF is the first one is non-preemptive, the second one is preemptive. But both schedule the processes based on a criteria. They give the priority to the process which has shortest time left, our shortest job first, right? So in priority scheduling, what we do is that we associate a priority number, or let's say an integer, with each process. And then what we can do is that we allocate the CPU to the process which has the highest priority. So which number, like let's say you have process A, B, C, D, and D, and they are given the numbers, let's say 0, 1, 2, 3, and 4, or 0, 1, 2, 3. Okay. So in some systems or some implementation, lower number means higher priority. Like a process with priority number 0 means it has higher priority in some implementation. But in some other implementation, people use a different interpretation where 0 lower number means lower priority. But here in this book and in this lecture, we are assuming that if the priority number is lower, then it has the process has the higher priority. Okay. So the CPU is allocated the process with the highest priority, smallest integer is equal to highest priority, and the process and this algorithm is preemptive. Preemptive mean that if you are currently running a process and another process arrives with the higher priority, then the currently running process is kicked out, and the process with the higher priority is run. And if in the ready queue you have more than one processes with the same priority, then you use first come first serve for to break the tie between those processes with the same priority. Okay. So SJF is a priority scheduling algorithm, but it is non-preemptive, where priority is the predicted next CPU burst time. And SRTF is also a priority-based algorithm, but it is preemptive one. Okay. Wrong spelling for the preemptive, but it's okay. So, okay, now I want you to do this on your notebook. So you have 5 processes, you have their arrival times, you have their CPU burst time, and you also have their priorities, right? And now what you need to do is that you need to draw the scheduling chart for them. What will be the scheduling order for these processes? And remember that lower the priority number means the highest priority. So here in this example, C is the process with the highest priority. Okay. So now on your notebooks, do the example where you need to draw the scheduling chart for these using non-preemptive priority scheduling. Non-preemptive. Sorry. Okay, anyone who has found the numbers or solution? If none, then okay, stop here and start working on preemptive priority scheduling. You can complete the solution later at home. Do the same thing, draw the scheduling chart using the preemptive priority scheduling. The solution is already given in the slides, but I want you to work.
Can we go over a little bit more over the difference between non-preemptive and preemptive?
So the difference between preemptive and non-preemptive is this one. Let's say a process A is already running on the CPU. It is already scheduled. And let's say it has priority X. Okay. And then another process arrives, process B, with the same priority, right? Now the question is, what should we do with the process A? Both now, the newly arrived process B also has priority X. In non-preemptive, what you do is you allow the process A to complete its execution, and then you schedule process B. But sorry, if let's say the B has the higher priority than A, let's say X is, let me give you this example more concrete. A has the priority number 1, B has priority number 0. So A was running, B arrived. What to do with the A? One option is let it complete, which is non-preemptive. Preemptive is we don't let it complete. When the B arrives, which has the higher priority, so we preempt A and we schedule B to execute. So we kick out the A and we run the B.
So for first come, first serve, we would just stop the process and put the other one running. And for round robin, we would wait for the
No, for first come, first serve, it will let the process that was already running to complete. Because it is first come, first serve. I came first, I got the turn, I am running on the CPU. You came after me, you cannot kick me out. Okay. This is preemptive priority scheduling. I'm not saying use round robin. Don't use round robin here. We are not using round robin here. I'm using schedule the processes according to their priority numbers and arrival times. Get it or not? Not? If not, I will do the example, then you will understand. Okay. Since I'm now like drawing more and more on the board and I'm talking like when I'm away from the laptop, the quality of the recorded lectures will not be as good as it was used to be for the earlier lectures, because sometimes I stop, I forget to start or resuming the recording. So now I resumed it, but earlier when I was doing the example, the recording was stopped and maybe it is not recording. Okay. So let's do this example for preemptive priority scheduling. Okay. You can do the non-preemptive on your own, and the solution is anyway included in the slides. Okay. So I have this timeline, and I have arrival times of 0, 5, 10, 25, 30, and this is A, B, C, D, and E. And okay, I also want to record here the A, B, C, D, E, their first time, so that I don't need to look at the slide. 20, 15, 20, 15, 20. Okay. At time 0, we have no ready process, but only process A, right? So I schedule this one and I let it execute until I have any other process ready for execution. So, okay, what is its priority? Its priority is 3, 2, 0, 1, 1, right? So at time 5, I have another ready process, and which is B, which has the lower priority than, which has the higher priority than A, because remember, the lower the number, higher the priority. Okay, lower the number, add the priority. So it has executed for 5 time units. So it has remaining bus time of 15. And now I select this one, right? So B executes for 5 time units. And then I have another ready process C. Now I look, so its remaining time is 10. Now I look at compare the priorities of the ready processes. So this one has now the highest priority or lowest number. So, okay. So then I schedule the C for execution and it executes for 15 time units, right? So remaining I have 5. Then at 25, D again arrives. D arrives. And I look at the priority, compare the priorities 3, 2, 0, 1. C is still highest priority. So I let it continue. So it continues and it executes for more 5 time units, which is 30 here. Okay. So C is completed at 30. So we are done with C. Then I look at the available processes. So we have 3, 2, and 1. So 1 is highest. So I schedule the D and sorry, at 30 I already have E also, right? So E is also like has the same priority level as the D, so I can choose any one of them. Let's say I choose D. Okay. So I allow the D to execute and it executes for 15 time units, so 45, right? So now this one is done. Then I look at remaining ready processes. I have E, which has highest priority. So I execute it for 20 time units. 45 plus 20, 55, 65, right? Then this one is also done. Then I look again at the remaining one. B has the highest priority. And it needed 10 more time units, so 75. And then this one is also done. So and then A, which needs 15 more time units, so 90. And A. Okay. Clear? So then if I ask you to find the finish time, the waiting time, the turnaround time, you can easily get them from the chart, right? So here is the solution for both, but there is a just little bit variation in the solution in the sense that we list a letter for every 5 time units. So like it is A. Like for example, for the preemptive one, it is A, B. Because first A took 5 time units, then B took 5 time units, and so on. So the same chart is not drawn, but in a different shape. Okay. Before we stop here, can you tell me something which is wrong with this algorithm? I mean, what is the drawback? What is the difficulty you face when you are implementing this algorithm?
It creates starvation. If the processes keep getting pushed back.
Yeah, that is possible. Yes, definitely. But I am looking for another answer. Okay. So let's say you have the processes, not only 5 processes, you have 1,000 processes in the ready queue. Now, if you want to schedule those processes according to priority, what will be the drawback?
You would have to go through all the processes to see their pattern.
Yeah, so you need to scan the whole list of the ready queues, whole list of ready processes to find a process which has the highest priority, and maybe it is the last in the queue. So there will be a huge scanning time, a search time, right? So we will talk about how we can handle this in a different algorithm, address that issue in a different algorithm. Yes.
Wouldn't you just use like a priority?
Say it again, sorry.
You just use a priority queue that's already sorted, so it already has the highest.
No, these are not priority queues. I'm saying ready queue.
Oh,
In
yeah.
the ready queue, you have processes that say A, B, C up to Z, but they are not. It is not sorted. It is like
I just comes in. maybe.
yeah. When it becomes like when it is kicked out of the process, you put it in the page.
Yeah.
So you are not retaining any order. Any question? Okay, then see you next week.